Hey everybody, welcome to the stream. Hope you're having a good Sunday. We are going to do some Sudoku solving, basically, today. That is the analogy that the author of the book, we're going through Essentials of Compilation and Incremental Approach in Racket. And that's the analogy that the author uses to talk about register allocation. To refresh, register allocation is the process of finding registers on your target architecture in order which to place variables that you have in your program. So since our program only has integers right now, we only have to be concerned with integer operations, and the largest size integer we can represent right now is 64-bit because we are targeting Intel x86 64-bit architecture. So all of our variables either fit into one slot on the stack or into one register. So last time we did the first half of Sudoku, basically. That was building the interference graph. So building the interference graph means that you look through all of the live variables and see which ones have to be concurrently live with them. So that means that you can determine that like these two things can't live in the same memory location. So in other words, they can't share a register, they can't share a slot on the stack. But if they're not in conflict, they could potentially, so they don't live at the same time, they could potentially go into the same register or into the same slot on the stack. So that's what we're going to do today. We determined the conflicts, and now we're going to go through that graph of conflicts and determine what slots are available, so what registers are available, and basically greedily go through and assign variables to registers. So when I say greedy, I mean the algorithm is greedy. Luckily, there's enough constraints on this problem that we don't need to do serious backtracking in order to solve it. So, that said, let's flip over to the coding screen. Last time we pulled in this graph library. Now it's only at 0.1.0, and we ran into a few things that bugged me. Number one, that the only identifier for a node in this graph is an integer, and what we want for our nodes are going to be a location, which is either a register or a variable. And so we had to I'll flip over the editor real quick. We had to have this lookup table, which is kind of wasteful. And is also going to make our, I think it's going to make our next pass a little bit more awkward. So what I would like to do first is we're gonna bring in this module. Note, it only depends on standard library modules, so we don't need to worry. There's some other code in this repository, but I don't think it's being used. There's this graph internal heap. I mean, it looks like a min heap. We might want to use that for a excuse me. Let me make sure that it's not used. But we might want to use something like that for a priority queue later. Except we probably want a max heap. Let's see if there's anything referring to heap in here. No. Okay, so that's just scratch code that they're not exposing as they're in the published library. But I want to bring this in and modify it, so I'm just going to copy paste that. And yeah, let's just make a new file called graph.gleam. And then we're going to go through and refactor this briefly. So what we're going to do is we're going to import EOC graph. It's basically the same thing. And we can get rid of this dependency from our gleam.toml. already updated the manifest for us. Cool. Okay, so a couple things we need to change here. Sorry, for a moment there I was about to sneeze. Okay, so we are only going to have undirected graphs. So we don't need the direction here. We might have to change... I don't really need to modify this documentation, but I'm going to anyway. Okay, so we're going to remove the direction, which was just a phantom type anyway, or a type marker. The other thing that we want to do is have a key type. So rather than that just be integers, so node is have to be parameterized by the key. Context will be parameterized by the key as well. And hopefully this shouldn't be a big refactor, but we can say, you know, pass through that type there and that there. So now our node has the key that we want. We're going to have to fix our interference graph on this, obviously. Okay, so this is going to be, you know, key value label, not direction value label. And this is going to be key value. Okay, that's fine. Let's look for other references to int that are part of the key. Yeah, so node ID is going to have to be key here, right? Okay, and key. Then we're going like all out generic here. Okay, so this is key value label of node key. Okay, and okay, we aren't. We're going to have to fix the context. And then here, there's no directed edges in our graph, so we're just going to say insert edge. We'll clean up the context later. And this is, you know, between our nodes, the keys are this key type, not integer. Okay. It's interesting that we weren't immediately getting some type errors here, but that's okay. Okay, we don't need to add outgoing. Well, that's an internal function, isn't it? That's not public. Right. Yeah, we'll fix this up in a minute. I want to fix all the type errors first. Hello, welcome from Brazil. Welcome to the stream. Thanks for coming. Just for reference, we are refactoring this graph module to be generic over the key type so that we can use whatever key we want. And then I'm going to definitely have to go back and... Sorry, that needs to be... I didn't realize... Yeah, okay. So we don't have directed edges. We do have undirected edges, but Okay, so key instead of direction. Right, so this is folding over the graph. We may need to use that. Map context. That's fine. Why does that produce a directed graph? Okay. Well, we'll fix that. I don't actually know why that was necessary. Okay, we're getting close to the bottom. All right, key. So that's just labels on the edges. We're not using labels right now. That's fine. Okay, so this is about directed graphs, so we can just delete that function. We don't care about directed graphs. That's fine. Okay, so let's go back and make sure that we don't need any of the rest of this. And I think that there were some cases where we needed to fix a few things. Oh, right. So our context, let's see if we can rename that symbol. Nope. Okay, so our contexts have both incoming and outgoing edges, but since we're undirected, we only need one. And we'll just rename that to edges. And then let's incoming. And let's replace that with edges. Okay, and let's find all the outgoing and just be rid of them. 39 places. Okay, so outgoing. Let's see. Okay, node ID has to be key. Yeah, there was an error there. Let's find other outgoings. So we don't need. Yeah, we'll rename that. Add edges edge. Okay, so we don't need to add an outgoing edge. That's not valid syntax. We're just going to say context. Context. Okay, so we need to go to that definition. Yeah, we missed this, so this is key. We can get rid of outgoing edge, outgoing edge. Here, I'm sorry, let's go back up to the beginning. This is becoming a bigger refactoring than I... Well, the edges, okay. Okay. Right, so this needs to be edges. And let's rename that to edges. Outgoing. Right, honestly, we could probably just jump to all the errors and fix them. Let's just scroll down here. Okay. There's some here. So update context. Okay, I have a problem with, oh, this needs to be key. That'll fix that. Okay, so we're going to remove that. Node ID. Right, so we'll do that. What's wrong here? It says expected dictionary int to context. Node ID is key here. I might be in the caller. Oh, no, it's in this. So this needs to be generic. Okay, and let's rename this. It's not going to. Okay, we don't need outgoing occurrences, not used. We don't have outgoing edges. We need to rename that. There are some cleanups we could do syntactically here. Okay, so yeah, again, I missed some places where it was int and it should be key. Clearing up a lot of the errors here. Okay, and here there's no outgoing edges, so we can get rid of that. Again, no outgoing edges. Don't need to do that. Okay, that's all the type errors. Let's look at the, yeah, so add edges, edge. Let's just, it really doesn't let me rename this directly. Okay, we're just going to say this is add edge. And then let's just add edges, edge, and replace that with add edge. And what was the other thing that was really, oh yeah, remove edges edge, right? I think it's because we did the rename of incoming to edges, and then it renamed it in all the function names too. So, oops. So we're gonna rename that to remove edge. Okay. Let's see if there's anything else that's awkward in here. Okay. I think this was incoming occurrences. So let's remove, oops, remove edges occurrences. And we'll call it remove. Just remove occurrences. Is there anything else in here? Remove undirected edge. Let's rename that. There's a problem though. I think we have an internal function called remove edge. Let's do one more rename on that. We'll call it remove edge internal. And then, oops. Let's see. And then we have remove undirected edge. We'll, since that's a public function, it's not called by anything else, we'll just call it remove edge. Let's see if there's anything else that's weird in here. Okay, so now we need to fix our interference graph, and luckily we can say that this, the key is now x86 location, which is huge, and we can get rid of this. And now we don't need that. Okay. So we don't need to looking here at insert node. Yeah, so this is fine. It'll just replace it. So we can simplify this. We can go insert node, and the node is going to be the ID is going to be location, and the value is going to be node of location for now. And then we just wrap it in our own interference graph type. So we can get rid of this. Much simpler. Okay, so this is just going to be insert edge. And we don't need these anymore, so we're just going to use A and B. That's nice. This should make it a lot easier. Okay, and this is going to be graph.hasEdge A, B. Okay, so let's make sure that there's not too much going on here. Yeah, so we're not using that anymore. We can just get rid of it. All right, this is good. Let's make a quick addition. Here, let's just add everything. We're going to refact pull in graph.gleam and refactor. That's just so we have a point before and after on this refactor. Okay, so now we've got the locations, and as the key of the node, which is good. That makes it going to make it a lot easier to do stuff with this graph library. So let's really quickly run our tests and make sure that they still pass. Okay, so we got some problems here. Values were not equal. All right, so we broke some stuff. This was in this. Okay, so let's look at, see what line was that? It did not say. Did not say which one. Oof, that's bad. Let's do Gleam update just to make sure we're okay. So we did get something. Okay, debug is, I'm not sure where we were doing that, but oh yeah, we're doing it down here. Okay, so unfortunately that broke some things. I want to look at, see if there's some tests in this. No, he doesn't have any substantial tests. So that's not helpful. There's a possibility that I broke something in that refactor where we just removed stuff. Okay, those functions are transforming the label and the value type. Okay, so their assumption here is that it turns undirected into directed, but we don't have that assumption here. The interesting thing is that there's no reason this couldn't map into new key types and value types and label types. So I think that, I mean, this is not going to make a difference because we're not using it, but let's look at our build interference pass and okay, so this is building the conflicts for each block. So we have the two rules about what happens when you see a particular instruction. It's either, if it's a move, then you have to look at the live locations in S and the locations in D. Otherwise, it's just the right locations in the instruction, which we had already determined in Uncover Live. Oops, that's the test. Excuse me. So we'd made these two functions public, the right locations. What's not clear to me is and I don't know how we can use this should to label. Let's look at those docs. Yeah, there's not. There's not anything about producing a label here. Right, they do panics, right? Which is what you expect from a test framework. You just don't get the context of what let's look at the FFI here. Okay, it's using eUnit underneath. And this is a macro, by the way, which is intended to be used inline, and it expands to like a case expression with capturing the actual, like the tokens of the expression. So not actually that helpful here, which is potentially part of the problem. Okay. So we're going to have to figure out which one of these statements is incorrect. And I think I'm just going to do print error. P. And I'm going to say W and V. And W and RSP. In here, X and W. I just want to make sure that we can find out what line. Print line debugging. Didn't think we would be here. This is Y and W, Y and X, and we have Z and RSP, Z and W, this print a line return? Oh, I know, I'll change this print line error in a second. Z and Y. T and Z. T and RSP. This is RAX and T. And RAX and RSP. Okay, so print error. Let's replace all of those with print line error. Oops. Okay. All right, and then we will run this test. And let's just focus this one in particular. Okay, so it was the first one. Like this very first conflict did not. So let's go to the has conflict. Okay, so it's just has edge from A to B. Right? Hi, Chris. Welcome to the stream. So yeah. So I think what I want to do here, before we get to this, let's, yeah, I know it doesn't, it's deprecated, but let's print out this graph because I want to see what looks wrong in the graph. And if it's just like we didn't add any edges because we broke the code, then I'd like to know that. Okay, so this is R10. Yeah, so let's find one that should have yeah, I'm not seeing any edges. All these edges contexts are empty. So I broke something. Broke something pretty serious. We might need to back this out and just deal with the fact that the author of that library decided the node identifiers should be integers, which like is fine if your structure that you're storing them in is like an indexable like list of some sort, array, but like in this case it doesn't make sense. It's a dictionary. You can use whatever label you want, whatever identifier. So let's no, like the graph lib is fine. I just did some refactor where I removed all the integer labels and made it generic over the key, so that we could use the locations either being registers or variables as keys, and it didn't like that. So let's scan through here real quick and see if we can see anything. Okay, so nodes, that's not going to matter. Size, that doesn't matter. Has node, right. We figured out it wasn't adding any edges, so we should probably look there, which is insert node. Okay, insert edge, calls update context. And this is fine. Why don't we simplify this real quick? And we'll do the same here. Oops, except it's this. Okay. Honestly, this looks so straightforward. I'm not seeing any problem. So adding an edge, this internal function, takes the edges out of the context. This should really be 2, but we're not calling it anywhere else, I don't think. Here, final references. Does that work? Nope. The Gleam LSP needs help. I wish I had time to work on it. We are... Yeah, we're just inserting... Okay, so looking at remove, we're not using remove edges though. We're not removing nodes. We're really just adding edges. So let's look at this and also our interference graph, which is a wrapper around that. So add conflict. We're inserting edge. Labeled between that and that. So this is the thing we're calling. Let's do a little bit of a test for this. I think that that's probably worth. Okay. So we're going to import Glee unit should. Interference graph. Okay, so we're going to say will and locations and so forth. Okay, the other possibility is that we need to make sure that that add locations doesn't destroy anything. That could be what's happening. Because I think we changed that. Actually, that might be the problem. Yeah. I bet this is the problem, because on every step of walking through the live after sets, we're inserting an empty node. So let's has node of location. If that's true, then we return G. If that's false, then we do this. Yeah, I think this is the problem. But okay. That said, I would still like to write a quick test. So let's do I didn't make this like opaque, so we can look into it. It's fine. I'm going to say g.graph graph.has node. And I just want to make sure that there's, we're going to have to get x86 base location. And we need, let's just pull in REX for now. Okay, this is a quick sanity test. Oh, interesting. Our test passed now. It ran the whole suite, not just this one test. Okay. Okay, I think we'll leave this test, but we just fixed the other one. So I need to go through and remove all of these. We're going to restore that. Remove all of these print lines. Okay, it was just, I thought it was the implementation or a refactor of that graph library, but it really was just the rewrite of the wrapper function, which made sure that all the locations existed in the graph, and honestly, that was silly of me. Okay, almost there. Okay, and that's fine. All right, so finally, you never know when you go to code something. You never know it's going to take you. It's always a journey. All right, so our next step. Let's get to what that was, and I need to open the recent. There we go. Nope. Book. Okay. So why do I keep talking about Sudoku? Well, what we built. So this is like the graph that we built, the interference graph. And you know what we did here is we drew edges between things that cannot exist in the same location. This is essentially like a strategy for doing Sudoku where you go, okay, so everything in this column that's not this cell cannot have 1 in it. Or everything in this square that's not this cell cannot have 1 in it. And that's what these, the edges here are signifying, is these two things cannot be equal, right? And so it's, so we've established what, in contrast to this diagram here, where we're only concerning ourselves with some cells of the Sudoku board, essentially in our program, we have all the cells. We've recorded all of them, right? So all of the variables, all the registers, and we've drawn edges between the ones that cannot be the same. So, there's some other things we need to do here. So we need to expand what's in our node. So we have the location, which is just, is it a variable? Is it a register, right? But we need to have some additional things here. So we need an assignment. And I'm going to break this out on multiple lines here. And we're going to start this with, Gleam option. Option, some, none. Okay, we're going to use those. Okay, so this is going to be option, and this is going to be an integer, and we'll see why in a bit. So we need to make sure that we know either this node has been given an assignment in our algorithm, or this is none, in which case there's nothing assigned there. The other thing that we need here in this node is the saturation, and this is a set of integers. So these are we're going to read here in a second about what this is, but just bear with me. I'm going to make these refactors. So this is going to be none and set new. Okay. And we need to we will do some adjustment on registers here in a minute, because registers are already placed, right? They already have an assignment, and we'll be giving them some integers there. Okay, so let's look at the book real quick. Okay, so some techniques for playing Sudoku correspond to heuristics using graph coding algorithms. For example, one of the basic techniques for Sudoku is called pencil marks. The idea is to use a process of elimination to determine what numbers are no longer available for a square, and to write those numbers in the square. So writing very small, obviously. For example, if the number 1 is assigned to a square, then write a pencil mark 1 and all the squares in the same row, column, and region to indicate that 1 is no longer an option for those squares. The pencil marks techniques corresponds to the notion of saturation. So, oops, wow, he jumps to the... Can I go back, please? Go back. So, careful when you click in this PDF. Okay, so the saturation of a vertex in Sudoku terms is a set of numbers that are no longer available for that square. So, saturation in our graph is... C belongs to the saturation for this node if there's a vertex adjacent to this node. So in other words, there's an edge, and the color of that vertex is C. So it's basically saying, what are all the taken colors on adjacent nodes in the graph, right? Right, so the pencil marks techniques leads to a simple strategy for filling in numbers. If there's a square with only one possible number left, then you choose that number. But what if there are no squares with only one possibility left? One brute force approach is to try them all, and so forth, and then backtrack. One good thing about pencil marks is it reduces the degree of branching in the search tree. Nevertheless, backtracking can be terribly time-consuming. One way to reduce the amount of backtracking is use the most constrained first heuristic. So in other words, choose the node with the largest saturation, or fewest possibilities left. The idea is that choosing highly constrained squares earlier rather than later is better, because later on there may not be any possibilities left in the highly saturated squares. Okay. Now, here's the kicker. Register allocation is easier than Sudoku. Because register allocator can fall back on assigning variables to stack locations. That means that instead of backtracking, we can be greedy. I mentioned this earlier in the stream. We can make the best choice at the time and keep going. We still wish to minimize the number of colors needed, so we use the most constrained first heuristic. Okay, so we're going to look at their algorithm for desatur. I don't know why they algorithms are always named like this. Anyway, it's from 1979, so I guess that makes sense. Everything was in caps and abbreviated. Okay, so in the pseudocode for this algorithm, we have a graph G, and what we want is an assignment color V for every vertex in G. Okay, so get the vertexes of G, and while we haven't run out of them, so we pick a vertex from W with the highest saturation, breaking ties randomly. So honestly, that just means like whatever order it comes out in, pick the first. Okay. Find the lowest color for C that is not in an adjacent color, which is essentially our saturation set, right? And then we assign that color to the vertex, and then we move on to the next one. Okay, so here's where we get to the integers I mentioned. So we use, okay, where do they say here? Just as in Sudoku, the algorithm represents colors with integers, okay? The integers 0 through k minus 1 correspond to the k registers that we use for register allocation. So all of these registers. In particular, we recommend the following correspondence with k equals 11. The integers k and larger respond to stack locations. So note that if we get 11 in our algorithm, it means that we've used up all of these and we needed to go to the stack. The registers that are not used for register allocation, such as RAX, are assigned to negative integers. In particular, we recommend the following correspondence. So I'm going to do that by hand, I think. And then they go through, like, walking through the algorithm here, which is basically this. So let's first, remember we added these things to our nodes. We need to make sure that all these registers get their proper all these registers get their proper assignment. Okay, so yeah. Okay, so what I want to do is I want to turn this into, rather than just a list of registers, I think I want to get it in the order that they have here. So let's split this so I can see both at the same time. Oops. I don't need to update you right now, Rectangle. Thank you. Okay, so let's get RAX up at the top, and then RSP, RBP, R11, and R15. I'm not sure why those are not able to be used in register allocation, but okay. Okay, and then we have RCX and RDX and RSI, RDI. I don't know why RBX gets moved all the way down there. Okay, R8, R9, R10, RBX, R12, R13, R14. Okay, so this is the order that they're giving here. And then we're going to do some line editing here. So I'm going to do I'm just going to do like so, and then we'll edit these. This is -1, -2. This is honestly in inverse order, but it's okay. -3, -4, -5. And then we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and now we're going to we're going to map this differently. Okay, I'm going to say reg color is pair, and then I want to do node. All right, now that this is done, we can pop that out. Okay, so we need to do something like this. Okay, we need to map this into our node, which is going to be our node is location, assignment, saturation. Location is going to be location register of the register. Assignment is going to be sum of the color, right? And then our here, let's pull this out. And then the saturation is going to be a new set. Okay, and then we need to wrap that in a graph node where ID is location and value is our node. I know it's kind of silly to have two, but we might need graphs for something else. Okay, so what's the error here? Okay. So we're going to fold over that, and then we'll wrap it in our own graph again. Okay. I kind of want to rename this so this is like IG or something, but so now we should have, and let's go here. This should still pass. Okay. Let me remove that unused Gleam IO. Okay, so all our tests still pass. That's good. But now we have let's just print it out here. I want to debug that. Let's see what that looks like. Right, so now, you know, our R10 has no edges, of course. It is R10 and right. Okay, so it has 6 as its assigned location and no saturation on it. All right. So now we've got the basics of the registers assigned in there. Let's look back at the book real quick. So if we go down here, the interesting thing here is that we need to update, I think, our add conflict to look at both the target and or like the source and the destination node, and if they have assignments, so like obviously RSP and REX are assigned colors already, that we need to insert that into the saturation set. So let's look in here, and okay, so add conflict. So I think what we want to do here is go and get the graph out, and then we'll do graph insert edge. There is a function in here like, yeah, update context. The problem is we need to get the node. Right, so insert edge was doing this, like adding edges. So I'm going to say we'll say let a color be graph dot what do we have available there? I mean, we have, do you have node? We don't want to remove the node. We don't want to map over all values. We just want to, maybe it's this match. We could match out both. Yeah. Graph A. Match. Yeah. And I really shouldn't use let assert here, but if we get into a situation where so that this is what we're going to be doing. What I want to do is get see, is there an add context in here? I think insert. Oh, well, there's get context. Why didn't I just use that? Jeez, Sean, making it so hard. Okay. That's a result. So let's do assert. Okay. Right. Get context of g.graph of A. B context graph get context g.graph of B. Okay, so now we're gonna do now that insert context is private. Make it public. I don't see why not. For this case, like, honestly, these should be in the same module, but here we are. So we want to modify a node without modifying the context. Can we do that without reprocessing the entire graph? Because we don't care about modifying. I mean, we could do map values. But then we have to go through, we only care about these two, right? I feel like there should be a modify node. Let's just make that function. And let's go back to what I made that public. We don't need to make that public. Really surprised there isn't a modify node. All right. We're going to make one. Okay, so this takes graph, key value label. We may get rid of the label later. And this takes a node ID, which is a key. And width is a like this. It's a fun, which is a function which takes, excuse me, a node key value and returns another node of type key and value. Okay, and this is going to return graph key value label. Okay. So what we want to do is context graph node ID. And if this returns OK context, then we'll do the thing. If it returns error anything, we'll return the original graph. Okay, so then what we will do is we'll take new node is context dot node and call the fun. And then we say insert context graph, and then we make a new context, which is the original context plus the node is the new node. New node. Okay, so that'll effectively replace the context. That's what we want to do. So we've got this, and honestly, we want to do can we do a splat like that? Yeah. Okay, so let's say okay, so we're going to insert that edge, and then we're going to do modify node A with a function which takes our node value, and if b context dot whoa right. Oh, okay. So the b context is this. So b context dot node dot is really not helping me out here, is it? So we'll get the value and then assignment. If it's sum I, then what we want to do is okay, obviously if it's none, then we would just return node. If it's sum, we want to do and then the value is going, we need to modify the value, right? This is getting a little bit complicated, but we're going to insert Okay, that was way too complicated. So much unpacking and packing and yeah. Maybe what we do is we unpack this one more level and go modify value. So where did we do that? Modify node. Maybe what we do is let's say modify value, and then that will cut down on one level of wrapping. And we can do the rewrapping here. So let's do, let's say new value. And then here we'll do node of the context.node, and then value is new value. Okay, so that's a little bit easier. And then over here we can modify value, and then we don't care about this extra wrapping. Yeah, it doesn't like that. Okay. All right, what's wrong here? Oh, I typed fun and not fn. Okay, so this is node.saturation, not. What is going on? Okay. So now it's complaining we haven't done that. So we need to modify. We need to do basically the same, but invert it. So we modify value at B, and if the A context has an assignment, then we add it to the saturation. Okay, so let's do, we're going to keep going back to this, and I should not remove that line. What I want to see here, oh no, wait, that's not right. We want to go in here, I think. Let's look at the conflicts here again. I want to see that it is filling in the saturation for the stuff with registers, right? Because the registers have assignments already, right? Okay, so let's run Gleam test. And all right, so we have to get down to our node, and we need to find, so like T, note that it has -2 and -1 in it already. That's exactly what it should be in here. And let's find RAX. I'm really bad at this. Okay, so here's RAX, and it has -2, which is RSP in it already, and it's assigned node1. So that is working correctly now. And we will comment that out just for sanity's sake. Okay. So that was a step. So we have filled all of these as we built the conflicts. So now we want to implement this algorithm. Finally, woof! So I think, or I thought that we would need a priority queue, but maybe what we will do is we will do it very efficiently. And then, maybe at a later date we can make this we can make this be more efficient at a later time. So let's make a function here that is we'll say next uncolored. Right, so this is picking a vertex with the highest saturation. Maybe we don't need this to be. Let's go ahead and make our pass here. Honestly, this is. Let's find out what they call the pass at the end of this. There's a lot of details walking through this. Okay, so we'll call it color graph. Yeah. So we'll call it color graph. And I was going to say this should maybe be part of assign homes, but we'll do that afterward. Okay. So this is probably going to have some of the same things. Yeah. We're going to need that. I don't know if we'll need this function yet. We might want... We might want to make a fold function which takes a graph and an accumulator B and a function from we're not sure yet. Okay. So if we've got the graph here, I think that this takes. We're going to take. Yeah, we'll just leave that. This could take x86 of R. Okay. So we're going to do something similar to what we've done before. We're going to say input.body. And then we're going to map values, and this is going to take that takes a function, doesn't it? Right. And ultimately we want to wrap it back up in a program. So this is going to take color graph block as a function, and then we'll make this in here. So this takes a block. And returns an x86 block. Yep. Okay. So our block, remember, has on it the graph. Complex. Okay. So at the end, we want to return the original block with the conflicts is, we'll just say new graph. And we will have, after this point, we will have colored every node in the graph. Okay. So now let's look at that algorithm again. I'm sorry, I'm looking at the what comes after. So then it's like you adapt the assign homes pass. Right. So this color graph comes before assign homes in the new, or they're calling it allocate registers. Well, boo. So I guess they're separating the color graph function from the allocate registers. So okay. Well, let's rename this whole file. That's probably a better name anyway as a pass name. So allocate registers, I guess I'm guessing like a portion of it is going to be coloring the graph. So that'll be an internal function. Let's just take the signature of this. Right. The thing is, though, I think in assign homes we did, yeah, so we went from x86 var to x86 int here. So I think that what we need to do here as well is, and I'm going to name this x86, and this is going to be x86 int as int. So this is going to take var x86 program and produce int. And we're going to take input body, and we'll dict map values, and so interesting. Its block has a body and a frame size, and not the graph goes away. Okay, so we're gonna allocate registers block here, and then we'll make that function, and then we'll do int.x86 program. We'll pipe it to that. Okay, so our function allocate registers block is going to take an input, which is a var.block, and it's going to produce an output, which is an int block. Okay. So you know, I think I'm going to go a little bit long today, because I want to make sure that we get through as much of this as possible. So we're going to get out of here the stuff that we need. So we have, in this block, we have the body, the live after, and the conflicts. So we only need the body and the conflicts. Okay. So we want to, so then what we'll do is we'll do, let's make a function that is color graph, and we'll say color graph conflicts. So that gives us the assignments. So I think that like there should be a step where we just color the graph, and then we should have a assignments, like extract assignments, which is really just going to map the nodes into a dictionary of location to location. So like variable to register, or and this means we're probably going to have to expand this to support stack. You know what? No, actually, I think we just need to do the reverse of what we did in here, like this. Because what we want is an arg, actually. And that's okay. That's okay. Okay, so let's do colored graph again. It's not this, right? What we want is this is going to take our interference graph and it's going to produce an interference graph because it's just modifying the nodes in place, essentially. And then extract assignments. And we may do this one first because it's going to be easier. And this is going to produce a dictionary. Yep. Way to go, LSP. Okay, so this is going to produce a dictionary from a location to an integer. And actually, no, it's going to produce an int arg because it needs to produce like a register or a stack location, right? A deref. Okay. So let's do a fold. We're going to take g.graph and fold over. We're going to give a new dictionary. And then our function here is going to produce... Okay, so that takes the context. So this is the accumulator and the context. And we don't need to pipe here because we're only doing one line. Only do one call. So we're going to take we're going to insert, first we're going to say let assert sum of the allocation is context.node.value.assignment, and let's call it assignment. We want to make sure that when we get to this point we have everything assigned, so I definitely want to panic if we haven't assigned something. So we're going to insert ID and assignment. Okay, so what's wrong here? Insert into accumulator. Okay. Gleam option sum. Oh, right. So we need to let's say assignment to arg, and we want this to be an argument. So this is going to take an integer, and it's going to return an int argument. Okay. So here's where we get to redo what we did in here, but in reverse. So if we do, let's see if we can make this any easier to edit. I don't think so. Let's do this. Let's see if I can make this a little bit less tedious. Actually, let's do get all the things that are the same length. Did you not cut? There we go. And then we will put parens on the end of there, and we'll get rid of some of the commas. We're getting close. Do the same thing here. Oh. What? Sometimes I don't know what my key combos are. Okay, and now let's get rid of all that goop. Okay, and we need to put some spaces back in there. It looks like I'm missing a paren up here. Okay, so now we're going to say stack, and here we're going to do deref of RSP, and then we're going to say this is stack because we know there's 11, right? And we know times 8, and then we need the negation of that. So oh, okay. It doesn't like parens like that. It wants brackets. Weird. All right, what's wrong with this? Int does not have a register value. Did I mistype that? Reg. Okay, that's easy to fix. Int.register. Let's replace them all with int.reg. Okay. So now we've got this, you know, we can map from the register or the assignment back into a register, because remember we were using integers to indicate what the assignment is. And then I'm sorry, my cat is shaking the desk. And then if it needs to spill onto the stack, then we know it's a deref off of RSP into the stack. Okay, so now let's do the actual coloring. Looking at the algorithm. Okay, so that what we did was just basically this. Wait, why is it RBP? Okay, well, let's use RBP. Just for consistency with what they say here. Yeah, they're using RBP. It's interesting to use the base pointer, not the stack pointer. I'm not sure why that is, but that's okay. We will learn later. Okay, so now we're going to implement their desatur algorithm. And I think that we're going to avoid the priority queue for now. And what we will do is we will just implement a way to figure out what the highest saturated unlabeled or unassigned node is, right? Okay, so okay. And we'll be able to use that, I think, that match to basically pop it off the graph and put it back on at the end. Because ultimately we want to have all of the graphs, right? The bit here that is interesting is that we need to, as we go through here, update the saturation on each of these nodes. I think this is just gonna get a little bit difficult. Okay, so I'm gonna type up the, okay, for all vertices in, or rather, that's essentially what we're doing. Because we're in a functional language, we're gonna have to structure it differently. But that's what we're up to. Now what we could do is when we pick a node, we pop it out of the graph essentially. And then when we've assigned it, so like we find the color that it needs to be assigned, we update all the neighbor nodes, adding that color to the saturation, right? And then we process the rest of the nodes in the graph. So we kind of maybe have two graphs going on, and we move the um, we move them from one graph into another, because once they're assigned, we don't need to visit that node anymore. Okay, so pick a vertex with the highest saturation. Okay. And then breaking ties randomly. So honestly, that really just comes down to when we find one, when we find one, we just pick whichever one we get first. Okay. And then it's find the lowest color, C, that is not in the colors of adjacent nodes. So in other words, in the saturation set. Assign the color C to the current vertex or node. Vertex, and then process the rest of the nodes. So really, this is what it is. So the trick here is that there's another step in here, which is update all neighbors, all adjacent nodes to include the assigned color in their saturation set. So it's going to be like, when we get the context here, we'll walk through all the nodes and do like modify value on them. Yeah, all the adjacent nodes. Okay, so we need to pick it's almost like we have a fixed point algorithm. We're not reapplying the same thing, but essentially we want to what did our extract assignments do? Yeah, no, we were folding over the graph in... The question in my mind is, do we actually need to reconstruct the graph? We might not need to. We might just need to return a list of nodes. This is like an unfold, right? We perform a function which produces a value. Yeah, is there a list unfold? Let's see. Oh, that's not going to help. Fine. Everything wants to update when I'm not watching. Okay, so Let's see, is there an unfold function in here? Unfold is like you have a generator function essentially. Fold until, no. Elixir has a great unfold function. It's just like it creates a stream, I think, or just something that implements enumerable, and as long as you keep calling, as long as it doesn't return, I think it's like, as long as it doesn't return error or stop or something. Now here's the continue stop, right? That's interesting. We might be able to do something like that. We have a dictionary inside our graph as well. That's probably not going to help. Okay, we're gonna have our to do until the end of this. I think if we are keeping this as a graph, all right, let's see if we can do something that we make like an infinite range or something. The other option is we take the size of the graph, because we're never going to have to do any. We're never going to have to do more iterations than the number of things in the graph. And we use like fold until. Let's try that. Okay, so we're going to do list range from 1 to graph.size of g.graph. Okay, and then we're going to list fold until. And we actually don't care about what's in this list. This is just give us enough iterations. And it's going to give us more than we need, right? Because if we don't find a vertex that's unassigned, then we're done, right? With the exception that we need to like pop off all of the things that are already assigned. So let me think about this. Our graph library doesn't have a, filter or anything like that. Now we could honestly make our own fold until, or hmm. Did we have a... We're gonna have to make some like private functions for this. I'm pretty certain, because we... I actually think that what we want here is a list of nodes. And then this takes... and then it's just list fold of G. And, oh, okay, so this is not a context, this is a node. And this is node.assignment. Node.location. That's simpler. Yeah, and I think what we want to do is like take that, take that value. So we actually need to do a step here, which is pop, or let's say extract all the nodes that are already assigned. I mean, it's either that or we are like we're going to have one color graph step function, I think. And this is going to take the interference graph. I'm sorry, I keep vacillating back and forth. And this is just going to do one step of this. And then what we want to do is I'm having trouble breaking this down in my mind because like the loop thing. And the problem is that what we want is like take a node off, which means we have the match. So we need to do again, this is like an unfold. We're returning an item and accumulator for the next step, right? I should name that module something way better. Okay. So, and this can be result nil. And what we want is if you call it, it's either going to color one node and return the remaining graph with modifications, or it's going to return error nil. And you just keep calling it until it returns error nil. Huh. And then these will be make part of the list. So it's like we unfold this function over the graph into the list. We probably need to make our own unfold combinator here. Okay, so this is going to take a function. We'll call this generator. This is going to take a function that takes an accumulator type and returns a result of an item type. Here, we'll use a bit more descriptive. Item accumulator or nil. And this is going to produce a list of item type. And then we need the initial, which is going to be the accumulator type. That's the combinator we need to write. And then this will be like unfold of G and color graph step. Oof. Didn't think I'd have to be writing this function. Let me make absolutely sure there's not something like this in Gleam already. There's this continue or stop type, which is nice, but Gleam function, identity, tap, no. Repeat. All right, I'm going to Google how to implement unfold generator. The other thing I can actually do, this is probably easier, which is we will look at the hex docs for Elixir. And we're going to look at stream, the functions, unfold. So how is this implemented? Okay, so it does a self-recursive function. We'll do something similar. And we'll just use result type instead of suspended and halted and so forth. They have a different okay, so they're actually returning a function, and then it's the all right, they've got this protocol back and forth with the enumerable, which calls into this. Okay, so we're going to have to make our own do unfold. And this is going to take, so next accumulator, next fun is going to be this. And then right, so this unfold is like consumed by a fold. This is a folder function. So what we need is a list, which is going to be a list of item. And honestly, looking at the signatures of these, we can just put that up here. Please, can I hit the delete key without looking at it? That would be nice. Okay, so we don't need this helper function because we're only going to unfold into a list. So this is a list of item. We'll call it result. Okay, so what we'll do is we'll say case generator of initial. And if it returns a result, if it returns an OK of item next accumulator, then what we want to do is call unfold next accumulator generator. Yeah, this is not as hard as I was making it. And we'll put item and then result. Okay. And then if it's error and we don't care, then we just return result. Why did I think that was that hard? Oh my god. Oof. Okay. So that's actually very straightforward, assuming you know what the target of the unfolding is. And in our case, we do. We don't, like in a general case, you don't. But this is actually not that bad of a thing, like that could be added to the Gleam standard library. So I may figure out a way to do that, like put it in the list module and have unfold, and have it be given a generator function. Yeah. And then it would be wrapped, like this intermediate result would be hidden And the other thing that you could do here is list reverse. It honestly doesn't matter for us though, so I'm not going to do it. But that's what I would do if I were doing this for the standard library. Okay, we're going long. I want to push through because I think that now that I've got this figured out, we can do one step, right? So I want to rename this because that is a pain. Ugh. Okay. We'll start there, 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 there. Not there. Okay. So just to note here, what we're going to do here is then we'll translate all the instructions with looking up their locations, right? Okay. Let's see. Okay, so if we have a graph, okay, so our first step is going to be we need to figure out what the vertex is. So let's, yeah, we're going to pick an unassigned vertex with the highest saturation. Okay, so what we can probably do is go we can do map values. Does that produce a new graph? Yeah, it does. Let's get the nodes. This is going to be okay. Yeah, let's do filter map. Break it out into lines. Because what we want in here is we want to ignore all the nodes that are already assigned. So So filter map returns okay, it expects a result, not option. That's interesting. Okay, so here we're gonna say error nil. And then if there's none, then what we want to return here is some indication of the size of the saturation, as well as what the ID is. So let's return, this is going to be OK of no dot value dot saturation. And this is going to be set dot size. Okay. And then we'll say node dot ID. That'll be sufficient. What's wrong here? Missing some parens. Okay. So then it's just like not used. Okay. So this gives us the list of vertices. And then here, let's go back to the Gleam standard library. So we want max, right? Most saturated. This needs to be its own function. Case pick vertex, and we'll do G. Pick vertex. And this, I think I'll do result of, and this is going to be location, or no. Could use option, I guess, but it honestly doesn't matter how location is ordered. We can just pick, you know, they said break it randomly. We're just getting what is the max saturated thing, where it's not assigned. And then we'll say we'll map for the OKs, result map. Pair.second. Does that not work? Oh, okay, so max needs a comparator function. Does pair have a comparator function? Does not. Well, let's just make this explicit here. Int.compare a.0 b.0. Is that not what we do? Oh, okay. All right. So this is returning what we expect. So if it returns okay, location, then this is the thing we're going to do. If it returns error, honestly, if it returns anything, we just return that because this will return nil, right? Okay. So now we need to take this location and we're going to modify the value. Okay, so I think what we need to do here is have a little function that picks the color. So and this is going to be the set is going to be set of int and that's going to return an int. And we need to start at start at 0. Start at 0 and try to pick those. So let's pick I'm gonna do one of these numbers because I'm feeling lazy. Set 0. Okay. I got out of the habit partly because Elixir and other languages I've been working in have such good combinators and things for working with collections that I just didn't have to do this kind of tail recursive stuff. You can have like infinite ranges and stuff like that, and it's just not in the Gleam standard library. So so we'll do set contains candidate. If it does, then we pick color internal of set and candidate plus 1 And if false, then we return candidate. And like this is a very basic way to do this sort of thing. That I just need to like remind myself of. Okay, so we need to look at the saturation set for this. Okay, so we're gonna take G. And we are going to do graph.modify value. And this is going to take our node. This takes the key, so yeah, I'm getting there. Okay, what happened here? Here, let me put another to-do in here so it'll stop complaining about the entire expression and show me anything that's... Okay, so this... Let me take a step back. What are you complaining about? Oh, I have to rewrap this. Or we have to return... Because it was like, hey, your return type sucks. Okay. Oof. That was causing a lot more trouble than I expected. Okay. So let's think about this. I actually I thought I wanted to do this, but what I want to do is do context, because we need the context of this location, right? So that we can get the edges and we can go update all the nodes that are pointed to by this, update their saturation sets. Okay, so new graph dot match right. Okay, So then this is the, yeah. So now we need to do some deep updates. So we're going to pull this out. Except this is going to be context dot node dot value dot saturation. Okay, and then we already have the color to yeah, we already have the color to update all the other nodes. So let's say new context is graph.context of that plus node is yeah. Okay, and then the value is node some color. Okay, so that's what we're gonna put into the graph. So let's do we actually need to create this node here. Yeah, let's do new node as a separate thing because we want to return this, right? Let's just call it value, and then we can do that. So that puts it back in the context without changing anything else in the context. And then we go new graph, and we're going to I'm gonna have to make this insert context public. I don't know why it isn't. Probably because accounting, like you want to make sure that the edges are correct. But then question in my mind, I need to look at the match. Does it, when it pulls it out, does it remove all? Yep, it removes occurrences. So I can't use match. Because that'll destroy the edges. And we don't actually need to insert this back into the graph, because we're removing it and we're adding it to our accumulator, right? So we don't need to reconstruct that. We just need to fold over. Let's take context.edges keys. We're going to fold over the keys because those are the nodes that it points to in the original, right? And then we'll fold over those with graph. I'm going to do this. And this is going to take, so this is a node identifier. And we'll do graph dot modify value. Haha, I'm glad I made this. So that's going to take G and node ID, right? And then the function here is, this is going to be our ig.node. Okay, so we'll say, and then we'll update the saturation. Is going to be set.insert saturation node.saturation color. So the color we just assigned, we update on all of the nodes that this had a conflict with. So like if it had a conflict with and it is probably best to show the thing here. So let's say we just picked a color for T. Then we know it has a conflict with RAX and Z and RSP. So we would be adding, let's say it picked 0, right? Which it will, based on our algorithm. So then T is 0, so we know REX. Now, the thing that I'm not maybe doing right here is that we don't need to update the saturation set for something that's already assigned. So let's say case is none node.assignment. True. If it's none, then we update it. If it's false, then we don't modify the node, because we don't if it's already assigned, we don't care about the saturation, right? Okay. So we mark 0 is no longer available for Z. Okay, so they're actually not, they don't care if it's already assigned. So they're actually putting it in the saturation sets of things that are already assigned. But you'll notice here that, like, on that step, Z will get 0 in its saturation set, so it will never pick RCX. Okay, so if we got that far, we've done all this. So let me get rid of this here. This is this. And then we assign C to the current vertex. And then we update all the adjacent nodes. And then we return, okay, the moment of truth. The item, so value, and new graph. Oh, we need ig.graph wrapping the new graph. I really need to get out of that business. Need to collapse those things. Okay. Wow. 420. I don't know if any of you are still here, but I've gone way over this time. So let's see what it's still complaining about here. What's the error? I was expecting this found. Okay, what did I do wrong? There, missing a paren. Okay, code is still incomplete. Fine. All right, so let's finish this up. So if we've extracted all the assignments. So now we want to create the new instructions, and we're going to list fold over instructions. Actually, we're going to list map instructions, and we will do let's say translate instruction with assignments. Okay. And in the end, we're going to do int block. I think we need to do. We need to figure out the frame size here as part of this. And I'm trying to remember what we did last time. Yeah, let's do that. Yeah. Frame size is going to be basically number of I'm going to put 0 there for now, but we need to figure that out. We can probably do it from the assignments. Okay. So we're going to translate an instruction, and this is going to be var.instructions. Yep. And the assignments, that returns, okay. It's an x86 location to an arg. And this is going to return an int.instruction. We're in the home stretch, folks. Bear with me. Okay, so we're going to have to branch over this, right? And this is going to be int.add. And what we want to do is we'll make another function, which is assign location or translate location. And we're just going to do this for everything. So call queue This is label arity. We'll just translate to int call queue label arity. Jump is label. That's int.jump label. Nothing to translate there. Move queue has A and B, and it's like this, except it's move queue. Okay. And this is neg queue. And then, yeah, we'll do that. Pop queue. And this is going to be push queue. And that's red queue, no argument. And then sub queue. Okay, so this is going to be A, and this is going to be A and B. Interesting how it reorders those. I guess that's alphabetical. That's fine. All right, so translate location is going to be another big case statement. Okay, so this is going to be x86 location. Or actually, it's not. It's going to be var.arg, is it not? Yeah, it's going to be var.arg. And there's our assignments thing. Again. And this is going to be a hint.arg. Okay. So if it's immediate I, then we have int.immediate I. If it's a register, then we have int.register R, right? Now it's a variable. So if it's a variable v, then we have again another place where we should panic. And this needs to be location var of v, and then we go arg. There's probably a more elegant way to do that, but I don't actually care what the string is, what the key is. All right. Now, last thing we're going to do today, an hour over what I normally do. Thank you. Still here for 420. Haha. Good one, Chris. Now that we've done all of this, oh my gosh. What I want to do is write a test like we normally do. So let's make an allocate registers test. Okay, and we're going to use the example we used for the interference. Um, and then what we're going to do is use what we have from the book. Um, we'll translate that into oops, allocate registers test. What I want is for our algorithm, now there may be differences with respect to like order of picking things, but I want it to produce the same output. We're going to lean on the fact that the interference graph is existing there, and we are already using that. So okay, and then we're gonna okay, and what I want to do here is actually what I want to do is turn this into what we expect from the book. Oops. So if we go all the way down here, this should be the coloring, and then we should get this. So this is what I want to reproduce. It's just going to be a little bit messy. Okay. So I want this to be okay. Okay, so we've got a block, and I'm just going to say 0 for now, but that's a to-do for sure. And this is going to be a list of instructions, and I'm just going to say P to allocate registers should equal P2, and I know that's going to be incorrect now. But at the very least we can get the test failing. Yeah, that's fine. What else? Okay, it's, yeah, they're not equal, of course. interesting what comes out of there. But we're going to ignore what came out of there because I want to see how it differs. Remember that the order there of picking which one is assigned to which spot is kind of arbitrary, right? So let's just reproduce this one, and here it's going to be deref deref takes what? A register? Oh yeah, I need to import RBP -8. And let's get this on a new line so I can see what the heck I'm doing. Okay, and then it's move Q 42 RCX. Deref RBP -8. No, there's some like pointless moves here, right? Which we would eliminate in the patch instructions pass, but that's okay. 7. Defer. Okay. I have a strong feeling this is not going to be correct, but we will see. And maybe we'll go back and we'll reread a little bit there. Okay, move Q. Here, we're always dereffing off of RBP, so let's do that. And then we're going to -16. Okay. And then we have another useless move. Oops. From 8 to 8. And then we have an add Q. RCX to our deref friend. Apologies, this is not the most interesting. I'm just transcribing. Okay. I am pretty certain this is not going to be correct, but let's find out what happens. Okay. They are not equal. So we move. So interestingly, what was expected was to move into RBP. Now it could just be that they say this is about assigning one register. And we're not making use of all of the registers in this case. Like we say K. First K colors to the K registers and the rest of the colors to stack locations. But we already decided that there were 11. So there's no reason why this should be correct. And I think that what we should do before we like go any farther is for all of these things that are one or two slots above the base pointer or below the base pointer because it's a stack, we should give them registers. So like based on the order of the registers that we gave over here, where did we do that translation? Right, so if it's 1, it's RDX. If it's 2, it's RSI. So we should expect that all the -8s will be RDX and all the -16s will be RSI. And I think that that's a pretty good assumption to go on. Here it's like, oh, we're only assign one or allocate one register, right? So let's change that assumption here, and we'll just make it okay. We're going to change all of these from deref into register. RDX, right? And then we'll import RDX, of course. RDX, RSP, or RSI, rather. Okay, and then all the ones that are -16. We'll change to RSI. Now, I don't know, maybe it's just for illustrative purposes that they choose to use only one register. But yeah, and we'll do the patch instructions thing again next time. Let's see if this tests. It works! What a journey. Okay. So for now, we're not doing this. I think I want to go, where's that? This test. We did a test with, yeah, that doesn't actually have any allocations in it. So there's no point. There's no point in going through that one. Whew. What a journey, folks. Well, if you're still with me, thank you for being with me. And I'm going to make a commit and push that, and then off we go. Okay, let's look at what we've staged so far. Okay, so we updated Gleam standard lib. That's good. Okay. Excellent. This is chapter 3.4, allocate registers. Okay, and that is all pushed up. Um, next time it's looking like we'll go through patch instructions again, which, note that we are moving some variables. Oops, wrong test. We're moving some variables into the same location that like don't have conflicts with one another. So we're getting these like move from register to register, like into the same register, and it's kind of pointless. So we can just remove them. And yeah, and so we will, and then we need to go back and do the prelude and conclusion. And here they're talking about frame alignment, which we will have to address by going back to this code and actually, instead of just giving 0 as the frame size at the end, we will need to take into account what are the callee save registers, as well as how much stack have we used in our assignments. And then that will be the frame size, right? So there's some more interesting bits in generate prelude and conclusion. This patch instructions will take like no time at all next time. Okay, so thank you so much, and we'll see you next week, hopefully. Bye.